Welcome to the introduction to section 4.3. Here it is, the section we've all been waiting for, the fundamental theorem of calculus. So I'm going to first introduce here a theorem we're going to need in our justification of the fundamental theorem without proving it. It's called the mean value theorem for intervals. It says if f is continuous on some closed interval ab, then at some point c in ab, f of c is 1 over b minus a times the integral. Okay, what does that mean? Well, I've shaded here in red the integral from a to b of f of x dx. And if we do a little bit of arithmetic here on this statement, it says that the integral from a to b of f of x dx is equal to f of c times b minus a. So it's really saying that at some point c, the area under the curve is equal to the area of some rectangle, where the height of that rectangle is f of c and the width of that rectangle is b minus a. So this is area under curve, under f, and this is the area of some rectangle. So I've drawn an estimate here. And I estimated that point C, and it's saying that the red area under the curve is equal to the area of this rectangle that I just highlighted in green. And that makes sense. I'm not going to justify it, but you could see that it would make sense that we could find some point there where that area under the curve and that rectangle have the same area or the same value. Okay, so here's our task. I've defined a function here, g of x. It's the integral from a to x of f of t dt. So this really is an area function. It's saying here, if this is my function f, here's f of t, this is a, it's taking an input x here, and this function is returning the area between a and x. Okay, so it says find the derivative of this area function. All right, well, I don't have any information about how to find such a derivative, so I have to go all the way back to the beginning of derivatives and use the limit definition. So g prime here would be the limit as h goes to 0 of g of x plus h minus g of x divided by h. Okay, so that's the limit as h goes to 0 of the integral from a to x plus h. Everywhere we see an x, replace it with an x plus h, minus the integral from a to x of f of t dt, all divided by h. Okay, so that means I'm taking, if this is x plus h, I'm taking the total pink area here in the numerator, and I'm subtracting out the green area, which means I'm just left with this piece of area in here. So that means that numerator simplifies to the integral from x to x plus h of f of t dt, all divided by h, and I can rewrite that as 1 over h times that area. Okay, so I pulled that piece out, not exactly the same drawing, but I pulled that piece out down here, that area from x to x plus h. And if we apply the mean value theorem for integrals, which was stated above, here the width of this interval is h, which is exactly b minus a. And so it says there's some c in here where that f of c is equal to this. F of c is equal to that value by the mean value theorem above. And so then g prime of x now is the limit as h approaches 0. I can replace that whole expression with f of c. And you may say, well, how do I evaluate that limit? Because that doesn't seem like there's anything that's changing. Now we come back over here and to this picture, and we're thinking about what's happening as h approaches 0. As h approaches 0, x plus h moves in this direction, which means c has to move in this direction. So x plus h is approaching x, which means that c must also be approaching x. And so this is just f of x. So what do we just show? Is that if we have this area function, its derivative is just the function inside the integral evaluated here at the upper limit of integration. And it doesn't matter what the lower limit of integration is. A is any number, and a didn't matter when I found this derivative in the end. Okay, So let's state that here because that is the first part of the fundamental theorem of calculus. So the fundamental theorem of calculus, part 1. If f is continuous on a closed interval, then that area function g of x, which is the integral from a to x of f of t dt, is continuous on AB and differentiable, and its derivative is just f evaluated at x. Okay, let's put that into practice a couple of times. We really use the first part of the fundamental theorem to help us justify the second part, but we can take some derivatives as practice. Okay, so here we have, I want the derivative with respect to x of the integral from 3 to x of 3t squared minus 6 dt. Okay, so the thing playing the role of a is 3. The thing playing the role of f of t is 3t squared minus 6. And the upper limit of integration is just x. So this says that this should be just f of x. So this is f of x, which is 3x squared minus 6. Okay, similarly, the derivative of the integral from 6 to x of 3t tangent t, really 6 is inconsequential. A doesn't play a role. The upper limit is just x. So this says everywhere I see a t, replace it with an x is what fundamental theorem part 1 says, and that derivative is 3x tangent x. Now though, I get things are a little bit different here. The upper limit of integration here is x cubed. Okay, well I'm going to define f of x to be this function. Integral from f of x to be this function, the integral from 1 to x of cosine theta d theta. Whether we have theta or t doesn't matter here. And what's the function that we have? We really have f of x cubed. That's the derivative that we want to find, is the derivative of f of x cubed. Okay, that looks like a chain rule. We take f prime, we evaluate it at x cubed, and then we multiply by the derivative, the derivative of that inside function. The derivative of x cubed is 3x squared. Well, what is f prime? Well, everywhere I see a theta, I'm going to replace it with an x. It's just cosine x. So evaluate that at x cubed. So we get cosine of x cubed times 3x squared. Okay, so there's what the chain rule looks like inside of the first part of the fundamental theorem of calculus. All right, so let's put the first part of the fundamental theorem to use in a more interesting way. So let's think about this thing, the integral from a to b of f of x dx. What is that? It's a definite integral. What is it asking for? It's asking for an area between the function f of x and the x-axis on the interval from a to b. It's technically asking for a signed area. We saw that if the curve function ever goes below the x-axis, that area is treated as negative. Okay, well, we just learned from the fundamental theorem part 1 that if g of x is this function, the integral from a to x of f of t, then g prime is equal to f of x. So what does that mean? That means that g is an antiderivative of f. It's a function whose derivative is f. So it is an antiderivative of f. That's by definition. Suppose that f of x is also an antiderivative of the capital F is also an antiderivative of lowercase f of x. Well, two antiderivatives we saw, I think when we were investigating the mean value theorem, that two antiderivatives must differ by a constant and only a constant. That means that f of x must be g of x plus some constant. Okay, well then we can get information about f of b minus f of a. F of b would be g of b plus that constant, and f of a would be g of a plus that constant. Okay, well let's write those things down. What is g of b? It says everywhere you see an x in g of x, replace it with a b. So that's the integral from a to b of f of t dt. And we have that constant, and now we had to distribute this negative. So minus g of a, What's g of a? Everywhere I see an x, replace it with an a. So that's the integral from a to a of f of t dt, and then I distribute, and I get minus whatever our constant was. Okay, well c minus c is 0. These things combine to be 0. What is the integral from a to a? Well, we saw a while back that that is also 0. So when all is said and done here, all that is left is the integral from a to b of f of t dt. It doesn't matter what letter I put there. Whether that letter is a t or an x doesn't make any difference, whether I call it the t-axis or the x-axis. So that is the integral of f of x dx, and we just, where did we start with? We started right here. So that integral is just f of b minus f of a for any capital F. What did we know about capital F? It was an antiderivative of lowercase f. Okay, this is it. Fundamental theorem of calculus part 2, the part that's of more interest to us. If f is continuous on AB and f is an antiderivative of lowercase f, then the integral from a to b of f of x is just capital F evaluated at b minus capital F evaluated at a. So now we have a much more efficient way to get our hands on areas. And so let's evaluate some. So let's just remind ourselves what we're looking for here. So this is the integral from 0 to pi over 2 of sine of x. What do we know about sine? At pi over 2, it's 1. At 0, it's 0. It's doing something like this. So this is asking for this area right here. Okay, so that means we need an antiderivative. So in this case, an antiderivative of sine. We need a function whose derivative is sine. So capital F of x, let's start here. In the statement of the fundamental theorem, lowercase f of x is being played by sine of x. Capital F of x then is a function whose derivative is sine. Well, the derivative of cosine is negative sine, so if I put a negative in front of that, I will get the derivative of cosine. So that tells me that this integral from 0 to pi over 2 of sine x dx is equal to f of pi over 2 minus f of 0. Okay, so that tells me that it's equal to negative cosine of pi over 2 minus a minus gives me plus cosine of 0. Let's see, cosine of pi over 2 is 0, cosine of 0 is 1, so that's 0 plus 1, or 1. So we just found that this area between sine x and the x-axis from 0 to pi over 2 has area 1 square unit. Okay, we can use this capital F notation all the way through, but it gets a little bit cumbersome, especially as we move further along in evaluating definite integrals. So I'm going to show you a slightly more efficient notation for these last two examples, and then you can try to put this into practice in the activity. So here's the slightly more efficient notation. Let's write down an equal sign. This definite integral is equal to. Now let's write down the antiderivative of x squared plus 1. Well, the antiderivative of x squared, we've seen that. That's x cubed over 3. And the antiderivative of x of 1 is x. And then let's notate where we need to evaluate this from. We need to evaluate from a lower limit of 0 to an upper limit of 1. Now, go ahead and do that. Evaluate at the upper limit. So here I'm evaluating it at 1. I get 1/3 plus 1 minus, I need to evaluate this at the lower limit, which is 0 plus 0. And that simplifies pretty easily. 1/3 plus 1 is just 4/3 units squared. So the area between x squared plus 1, we can draw a small picture here to remember this is going through 1 and 2, and this is 1, and it's a parabola, and we just found that area to be 4/3 square units. Okay, same thing here. Write down the antiderivative of x to the 1/2. So we add a power. That gets us to x to the 3/2, and we multiply by the reciprocal of 3/2, which is 2/3. So we get, sorry about that, 2/3 x to the 3/2. And we need to evaluate that from 1 to 9. So that is 2/3 of 9 to the 3/2 minus 2/3 of 1 to the 3/2. Okay, that second piece is easy. That's just 1 times 2/3, which is 2/3. And let's see, 9 to the 3/2. The square root of 9 is 3. So that's the square root of 9 raised to the third power. So 3 to the third power is 27. So that, man, that's 2/3 of 27 minus 2/3. Well, that's 2/3 of 27 minus 1. Or we can think of this as 18 minus 2/3. So that looks like 17 and 1/3. Is that right? 27 divided by 3 is 9, times 2 is 18. 18 minus 2/3 is 17 and 1/3 units squared. Okay, see if you can use that information to help you evaluate the integrals in the section 4.3 activity.